how do you create these specifications, you know, with different properties? So last week we saw perfect failure detector and eventually perfect. Okay, P and eventually P. And P has two properties. So this is the specification of perfect failure detector. Eventually, every crash node is permanently detected by every correct node. That's completeness. That means it never forgets any correct nodes. And accuracy, it doesn't make mistakes. So if you detect P, then you mean it really has crashed. If you think it's crashed, it really has crashed. So there's the strong completeness, strong complete, and strongly accurate. Strong accurate. So strong complete means that it sees all the crash nodes, all of them, no exception. And strong accurate means no mistakes. That means if it thinks it's crashed, it's really crashed. And eventually P has a small difference with this. So this is like the same. So if you look at eventually P, it's almost the same, except here it's eventual strong accuracy. So it's allowed to make mistakes in the beginning. Strong complete, and eventually strong accurate. Okay. That means, so this is a very important addition between these two. That means it's allowed to make mistakes in the beginning. Eventually means after some finite time, which we don't know, we only know it exists. After some finite time, no more mistakes. So that's the difference between this. So P never makes mistakes. Eventually P is allowed to make mistakes in the beginning. And both of them are strongly complete. That means they see everything. If a node crashes, they will see it. Here, no mistakes. Here, eventually no mistakes. Okay, so we saw it last week. So now, this is the start. This is like the starting point for today. So what I want to do is do some kind of experiment on creating a new kind of algorithm. What I want to do is leader election. Leader election, so intuitively it means I have a bunch of nodes and they elect a leader. That means they all choose one node as the leader and they all choose the same one. So we want to write the specification for this. We want to write the specification for this. So I'm going to write the specification inspired by this. Okay, here we have two properties, So leader election, actually, we'll see, it's actually kind of similar to P in some interesting way. And so we can inspire from this specification to get a specification of it. Okay, so leader election is actually somehow similar to failure detection. So failure detector detects the failed nodes, but the leader election is also a kind of failure detector. It detects a correct node. So here we consider like the leader to be like a single correct node that it detects the same for everybody. Yeah? Okay? So the leader detector is a kind of failure detector. Maybe it's not a very good one, but it is a kind of failure detector, so we can inspire by the failure detector definition. So it always suspects all nodes except for one, which is the leader. So it thinks all of them are not leaders. All of them are bad in some way. They're non-leaders except for one, which is the leader. And then something with respect to that node, basically that all the nodes have the same leader somehow, okay? So what I want to do is define an algorithm. These algorithms actually have names, okay? There's LE, they actually call, this is the standard kinds of names for this algorithm. LE algorithm, which is leader election, which we're going to be inspiring from P, perfect failure detector. And then there's the eventual leader election, which is allowed to make mistakes in picking the right leader, but eventually it has the same leader. It means that maybe in the beginning, two nodes pick different nodes as the leader, so it's like a mistake. Yeah? They're supposed to have the same leader, but eventually they'll have the same leader. This algorithm, for weird reasons, is called big omega, okay? So, historical reasons. It's a leftover from the 90s when distributed system was a real jungle, weird field. So this is kind of weird notation left over. So this algorithm, this one, is actually called omega, okay, for some weird reason. Because the first time somebody invented this algorithm and published it, they called it omega, okay? So let me now do the first step. I'm going to inspire myself from P and move to LE, okay? So you have to be a little bit creative, you know? So what does P do? So P, here I repeated that. P is strong, complete, always eventually detects the failures, sees everything, and it never makes mistakes. It never suspects correct nodes. Okay? Sees everything, never makes mistakes. So we can also have LE have completeness and accuracy properties. Kind of similar. So we're actually going to inspire from P to create LE. So what is the completeness of LE? Well, you always see everything that basically you always elect a leader, and if the leader has crashed, you get rid of it. So eventually, every node has a leader, okay? Every node trusts some correct node, okay? So some correct node, which is like the leader. See, this is like completeness. Every correct node has a leader, so nobody is missing the leader, okay? Okay, so that's one property, and now we go to the other one, the accuracy. So the accuracy is you don't make mistakes. If you suspect a node, you never ditch a correct leader. You never suspect a correct node. That means if a node is a leader, you will not get rid of him. You will never ditch or suspect. You have to kind of change the way of thinking in terms of suspected nodes and nodes that are not leaders. Okay? So here you will not suspect the node that's correct. Here you will not suspect or ditch a node that's a leader. Okay? So you can write, the way you can formalize this, no two correct nodes trust different correct nodes. So no two correct nodes. If I have two nodes that are correct, if they have different leaders, then that's a mistake. Okay? So two correct nodes, the trust is like the leader. That's what they think is the leader. No two correct nodes will have different leaders. That's a mistake. That's like, if they would, it would be a mistake. So this actually corresponds to never ditch a correct leader or never suspect a correct node. Because if they would trust different nodes, then they have to somehow change. Okay? So if two nodes trust different correct nodes, one of them has to move because they have to go the same node. Okay? So the way to say that everybody is the same is to say that no two correct nodes are, that none of them are different. Okay. So this is the way that you can say it in the specification. No two correct nodes trust different correct nodes, because if they did, it would be a mistake and it would not be accurate. So that gives us two properties. Eventually, every correct node trusts some correct node, which is the leader, No two correct nodes trust different correct nodes. So that makes two properties for LE. Okay? Eventually, every correct node has a leader, or knows the leader, has a leader. No two correct nodes have different leaders. Okay, so these two properties are inspired by this complete inaccuracy. Yeah? So this is completeness. Every node has a leader, and this is accuracy. No two nodes have different leaders, otherwise it would be a mistake. Accuracy means no mistakes. Okay, so this gives us a specification for LE. And we can write code from this. Okay? So you see kind of how it works. So usually when we make specifications, it's very good to start from one that you have already. And inspire yourself to a new one. Okay? Okay, now I'm going to do a little bit more. I'm going to do a little interesting specification engineering thing. I'm going to actually add a third condition to this, because these two conditions, I'll see, maybe are not completely good enough. Okay? So here's so far, our specification. Eventually, every node has a leader, and no two nodes have different leaders. So that seems very intuitive, right? I mean, the inspiration seems to be nice from P. But if you look at this, here's an execution where you run election of a leader. So I have three nodes. So, and P1, P2, P3, and they elect leader. They're running the algorithm, but one of the node crashes. P3 will crash here. So assume they elect P3, okay, and then P3 crashes. Now, here it says, no two correct nodes trust different correct nodes. But P3 is not correct anymore. That means if P1 changes, they have to change. Okay? P1 and P2, they cannot stay with P3. They have to change. But if P1 changes and says P1 here, then it's still correct. Because P3 and P1, even if it's different, P3 is still, it's crashed. But this one can change a second time. It can make P2. In fact, we can do lots of changes before this one, P2 picks a correct one. So as long as P2 is thinking that it's P3, which is a crashed node, P1 is able to change. But this is not so nice, okay? Nodes that are changing. I mean, it's correct, right? In some sense, it's still correct because P2 is not trusting a different correct node. It's trusting, it's P3 which is crashed. So the specification is maybe not quite good enough, okay? So so you might say it's a kind of mistake, it's kind of inaccuracy. P1 is allowed to change here. As long as P2 is thinking about the bad one, P3, P1 can change. So maybe we want to add another condition to not allow this, okay? So this is an extra thing. So basically what we do is we take these two conditions and we actually see what it gives. We make some execution and we say, is it good enough? Is it good enough? Is it behaving exactly like we want? I mean, the second condition is basically saying no mistakes. Huh? That's what we want. We want no mistakes. And we want to always, all nodes know a leader. Huh? All nodes have a leader. And here we have no mistakes. Basically, it means they have the same leader. But here you can see the problem, because we're talking about correct node. So a leader has to be a correct node, a node that hasn't crashed. Huh? A leader is has to be correct. So here you can see the subtlety that adds when you start having failure possible. So there's actually some extra subtlety because of the failure that's possible. Because of crashes. Okay? So maybe P2 thinks that P3 is the leader here, but P3 is allowed, it's crashing, it crashes, okay? So P2, it has to change this one, but it's not allowed to think this one anymore, okay? It has to elect another one, P1. But P1 here is able to change leaders. It can elect P1, it can elect P2, and it's allowed to change things because P2 is thinking about an incorrect one. So this condition is like not strong enough somehow. In some sense, we really want no mistakes, but you might say this is a kind of mistake. Huh? Maybe we want to avoid this. Now this is following that specification. Huh? So maybe we say it's okay, but maybe we want our specification to be a little bit better. Okay? Maybe we want to say P1 is correct here. And maybe I want to say don't change the leader if the previous one did not crash. Okay? If P1 is correct, then don't change it. See, this specification allows that. You see, it's kind of subtle. Huh? You see it because of execution. You follow the execution. And the subtlety typically happens because you can have crashes. And the specification is talking about correct nodes. Okay? So we add an extra condition to get rid of this possibility. If a node is elected leader, all previously elected leaders have crashed. That means if P1 is elected leader, I can only elect P2 if P1 crashes. It means I'm not allowed to change it if the previous one is still alive. Okay? That's reasonable. That means it's not going to be fluctuating. Okay? So this is a third condition that we add here. So this gives us 3 conditions. You see, we did it in 2 steps. Leader election. We started from P, perfect failure detector, and we got inspired to make a first specification for leader election. And then we looked at it and said, maybe we need a little bit more. Maybe this is not good enough. I mean, it's okay, it works. But maybe we want something a little bit stronger. We want an extra condition because of the crashes. If a node is elected leader by PI, all previously elected leaders by PI have crashed. That means you cannot change the leader unless the previous one crashes, which is reasonable. Otherwise, you might be changing, and changing is like a mistake. Yeah? You want to elect the right leader. So you can only change leaders if there's a crash, if you're forced to change leader. But if there's no crash, then there's no need to change. And that gives a third condition, okay? So that if a node is elected leader, previous elected leaders have crashed. So basically, don't change unless the previous one has crashed. Don't change leader unless the previous one has crashed. Okay, that's another way of saying this. The previously elected leaders have crashed. It's the only way to have a node be elected leader. So this condition is so that you don't flip-flop. Okay? This previous condition allows kind of flip-flopping between leaders. And this gives us a code. So I'm going to show you the code for this now. So this is the interface. So there's only one message coming back LE leader, it's like the crash message for failure detector. This black box will tell me who is the leader. And if somebody crashes, it'll tell me another leader. But there's always going to be a leader. And it satisfies these three properties. So that all nodes have a leader, that two different nodes will always have different leaders, correct nodes. And here, no flip-flopping, okay? You can only change leader if the previous ones have crashed. And then you can write the code for that. And the simplest way, I'll show you, it's very simple code. The way to do it is to rank all the nodes. So all the nodes have some ranking. Some are higher priority than others. For example, P1 greater than P2, greater than P3, greater than P4. And you have a ranking function that returns all the nodes with higher ranking. So we're going to try to elect the highest ranked node to be the leader. It's like the inheritance to the throne. If there's always an order, like in the UK, if the Queen Elizabeth dies someday, the next person in line is Prince Charles. So he's the highest ranking, and then there's Prince William, and so on. So there's a whole list of succession. So the ranking function is like that. It returns. So the rank for the highest node, ranking node is empty set. There's nobody higher. So this would be Queen Elizabeth. The rank for Prince Charles would be Queen Elizabeth, and so on. The rank for Prince William would be Elizabeth and Charles. If you want to do that royal family thing. So with that, the code is very easy. So here's the code. So this is leader election. It uses perfect failure detector. So basically, we're going to build it on top of P. So the code will look like this. You have a P code, an LE code, and indications going up. See, because we inspire from the specification of P to get the specification of LE, it means that in many cases we can also build LE on top of P, okay? So we use perfect failure detector as the base. So basically you have a list of suspected nodes. Basically you know they're crashed because it's a perfect failure detector, okay? So we take the highest ranking node, and that's the leader. If we have a crash, we add the crash node to the list of suspected nodes, and here we have the condition that gives us the new leader. We take a node such that R of P is suspected, so all higher ranked nodes are crashed, and P is not crashed. PI is not crashed, but all nodes that are higher ranking are crashed. So this PI is the highest ranked node that is not crashed. So this is a Boolean condition. And anytime this condition is true, we will execute this. So if this condition is true, then PI is the leader. So if one of these nodes crashes, if poor Queen Elizabeth crashes, then Prince Charles will be the one being the new leader, okay? So that's how the code, that's how it works. So that's leader election. So it's very straightforward code, and you build immediately on top of perfect failure detector, okay? And now, so that's LE. Now we can go look at omega. So this is the eventual version. So this one is allowed to make real mistakes. LE does not make mistakes. Whenever it knows it elects a leader, it's the leader. But omega is allowed to make mistakes. They only eventually have to agree on the leader, okay? They only eventually have to agree. So basically the properties of omega are coming from eventually P here, eventual completeness. So eventually trust the correct node. This one is always eventual. The completeness one is always going to be eventual. The agreement in the original LE it's not eventual, but in the omega it's eventual, which means that you're allowed to trust different correct nodes in the beginning, but after some time and no more. So this one will never do that. It will never make a mistake, because if there's any difference, it's because you have crashes. If two correct nodes trust different nodes, it's because one of them has crashed. But it will never trust two different correct nodes. But here it's allowed to trust two different correct nodes. Okay? And we don't actually need the third condition anymore, because here we're allowing the mistakes. Okay? We don't need to have the third one. So you have the specification. It's very similar to the omega. You have just one indication coming up. And here you use the eventual perfect in the implementation. And the properties are basically almost the same as the ones for eventually perfect failure detectors. Okay? And the code also is very simple. Okay, actually, we can get the code immediately from the eventually perfect. We thought we have nodes that are suspected. Okay, each node trusts a node with the highest ID among the nodes not suspected. So basically, the highest one that is not suspected, and all the higher ones are suspected. Okay, but it's allowed to make mistakes. So here's the code. It's almost the same as the code for LE. So you have a set of suspected nodes. You start by picking the highest ranked node. And then here you have two possibilities, suspect and restore. Remember, the eventually perfect failure detector can make mistakes. I think PI crashed. Oh, no, actually PI is correct. Okay? So it can correct mistakes, whereas the previous one never made mistakes. So, and then here you have a condition which is exactly the same as before. So we take a node such that all higher ranked nodes are suspected, but the node is not suspected. But here, it might be a mistake. Yeah? Some of these suspected nodes might not be really crashed. So here, if we elect this leader, it actually might be a mistake, because the eventually perfect failure detector can make a mistake. But because we know the eventually perfect failure detector only makes mistakes for finite time, after that no more mistakes, once it starts being correct, completely correct, then this one will also be correct. Once it corrects all the mistakes, the eventually perfect failure detector, then this condition will be correct. As soon as the suspected set only contains really crashed nodes, then this will be correct. So this is going to make some mistakes in the beginning, because the eventually perfect failure detector makes mistakes. But once this one stops making mistakes, then the eventual leader will also stop making mistakes. Okay? This is actually a pretty subtle algorithm if you think about it. In the 1990s, this algorithm was a research result, okay, published in a big conference. Now it's just exercise in a course. So basically, building it on top of eventually perfect failure detector makes the code very easy. In the days when failure detectors didn't exist, people didn't know about failure detectors, you had to reinvent the concept of failure detector each time you did a new algorithm, okay? So when I create eventual leader detection, I invent this thing, I publish a paper on it, I basically reinvent the idea of eventually perfect failure detector. But now, if you have eventually perfect failure detector, then this eventual leader detection is much simpler. Okay, you see? So eventually perfect failure detector is actually a really nice thing. It's a really powerful thing. It lets you make simple algorithms. So this simple algorithm does eventual leader election. Okay? So this has all been a little bit subtle, so I recommend you read over your notes after. And then there's one final thing. Let me say something about crash recovery. Remember, crash recovery, the node can crash and come back. and it has some stable storage, but it has some amnesia. Maybe it forgets some things, but it has some like this, so it can come back. It can crash and come back, like a zombie. But no, real, it can be really resuscitated, okay? But we have to be very careful. If it crashes and recovers forever, then it should not be a leader because it's bad. So how can we make it so that the bad ones, so the ones that crash and recover infinitely often, we don't want to elect those as leaders. So in order to do that, we can make a small extension to the algorithm. We add a new idea called epoch. So basically, each time you crash or you resuscitate, it's like a new epoch, a new era. So you can count that in your stable storage. When you recover, you have like an init event, a recovery event. So the nodes, they know how many times they've been resuscitated. So the leaders should be the ones with the lowest epoch. So we can add the epoch to the node ID. So it's part of the ranking. So basically, this is the same algorithm as before, except that the ranking also takes epoch into account. And we have to do the lowest one, because if we have a bad node that's crashing in recovery so very often, the epoch is going to go very big. So we don't want to pick this one. So we're only going to pick nodes with a low epoch. So the epoch is the first part of this pair. So the epoch has to be low. Okay. So the algorithm, you can actually extend it easily to work on crash recovery. So the same one that we did here, this one, this works for crash stop. Crash stop with eventually perfect failure detector. You can actually, by adding epoch, you can extend it for crash recovery. So you can do leader election on on a disk system, for example. If I have a distributed database with many disks, okay, then it's nice to have a leader node, because that leader can coordinate things. It can be like the boss and make things work well. So you need a good leader election algorithm. So this algorithm can be used for leader election for like distributed database. Okay. So that's just the final comment. Okay, that's actually all I want to say today. I think that's plenty. It's just getting into this notion of thinking about specifications, about what it means, about the code specifications, inspiring yourself from existing specifications to make new ones. Okay? So in general, in this course, we're going to see a lot of specifications, and you should always use those as inspiration when you make new specifications. Okay? Specification is very subtle. A specification is like an extremely high-level programming language, a specification. So this defines completely the algorithm. It's very dense. Every word here is important. So once you have a good specification, you should use it as inspiration, okay, for new ones. So whenever you want to make a specification, look at existing ones, okay? So in this course, we're always going to be building our specifications. We're going to do lots of inspiration. And it's not obvious, okay? Don't think that specifications are easy things, okay? They're not easy things, okay? They are very dense. It's like the most dense kind of programming that you can do is to write a specification, okay? It's very dense, but it's very concentrated information. So being able to think about specifications is important. So we're going to do a lot of specification engineering in the course, and I hope some of it you learn it. So once in a while I give you some exercises to do. Okay, so that's all for today. So I stop here. So you see how easy it is? Well, it's not that easy, actually. The code, after all that discussion, you have this very simple code. But this very simple code satisfies the properties. Huh? So the code is very strong, actually. It looks simple, but it's very powerful, okay? And code that we see now in one lecture, 20 years ago, it was like research results. Okay, so you're going to see a lot of things that were previously considered to be like publishable research results, like this eventual leader election. With the failure detector, it becomes very easy if you do it in the right way. Huh? This is very straightforward, right? I mean, you can get the intuition of this code. Huh? But if you don't have the failure detector, it gets much harder. Huh? The code is much harder. Try it without failure detector. Okay? So that's all for today. I hope you got some good intuition there. So the video is okay.